So this is a very good summary. By knowing the initial states, which means the initial Y ratios, the initial stress. When the Y ratios also mean density. So if you know like the initial density, if you know the stress, then pretty much you know like one data point. And also knowing the stress history help you, because sometimes like you're not on the normally consolidated line, but you may have a rebound going on. You're on the overly consolidated line or consolidated line. So that's why like you will also want to know about the OCR, the stress history. One more time, the key concept here is always knowing where to start and knowing where to end. So you kind of start giving you some constraint when you try to do the modeling. The modeling now we are talking about is the stress strength behavior of the soil elements. And if you have many soil elements add up together on the same site, at the end of the day, you can predict the performance. Like, you know, the end product you think about it nowadays could be, you can even like watch this on YouTube or wherever. And many people like this, they start to share their modeling results. Could be model the whole thing, like when a slope fell, how when a slope failure happens, how much deformations you are envisioning, you are predicting. So and everything like all those modeling, either slope or like a foundations, or maybe liquefactions when it happens, how the ground fell, how the soil mass slide. You know, those are the ultimate goal what we're trying to do here. Of course, like, you know, this is can't just like whatever we learn here, critical states of mechanics, is pretty much just the first page out of like a 1,000-page book. You know, you need to go you need to go deep, like, you know, even maybe get a specialized PhD in numerical modeling in order for you to go that far. But that's the ultimate goal. Try to model the whole ground behavior. But like to get that start, first you describe like each of the ground into like a small elements, and now we're talking about each soil elements. How would the soil behave? And in order to do that predictions, do that modeling, the first constraint you do is knowing where you start and knowing where you end. So the starting point we keep talking about this. The starting point very likely is the normally consolidated line. Is the normally consolidated line. So the NCL or the OCL. So now if you have a rebound going on, then it will be the overly consolidated line. So that will be the starting point based on like a stress history, whether either the green or the blue line here on this slide. And where it ends is always stop at the critical state line. So knowing all those like parameters, the initial state, it helps you to form a pond. And knowing the soil constant or the soil properties, which is like the slope of the line, so which is C sub C or C sub R. So C sub C is the compression index for the normally consolidated line, and C sub R is the recompression index for the overly consolidated line. So you know a pond from the initial state, the density and the vertical stress, you know a pond, and you know slope. Pond and slope give you the line. So you can start like constructing the critical state, the critical state line, the normally consolidated line, overly consolidated line. So having all this like start point and end point, then the next step is your stress path. And the stress path will depends on two things. The stress path depends on two things. The first thing is the stress history, whether you're normally consolidated or overly consolidated soils. So you need to know that. And also the drainage conditions, drain or undrain. So knowing these two like scenarios, and also knowing the start point and end point, then now we can start talk about the soil behavior, the modeling part. But like the fancy computer model, like, you know, you'll be way beyond like this class lecture. So like the expectations, the learning objective for this course is for you to understand the framework of critical state soil mechanics. So when we work on examples today, hopefully, and also your homework 5 hopefully give you a better idea on what is the expectations of this course, because this topic can go deep. till at the end, like you can even get like a PhD, and you can get like specialize your expertise in this subject and make a very good like career out of it. So, but that will be down the road for many years to come. But anyways, we stop here on Tuesday. So we talk about the equivalence like a stress concept. So we were talking about that we have let me have the most here. So we have the normally consolidated line, and also we have the critical state line. And like at some point there's a rebound on the normally consolidated line, which is the blue line right here. So starting from the blue line, we pick a point, and then like the equivalence, like a stress concept telling us there could be a mirror image, a mirror stress point, a mirror to this point, because like from the start we always know where we end, right? So for the undrained loadings, for the drain loading, a constant density, so you restrict the stress path only go like horizontally, and you know where it start, you always end at the critical state line, so you must go to the right hand side. So from this is the starting point to the ending point, so that would be the stress path. And the equivalent stress concept tells us there's like a mirror image. So the same equal distance from the other side, you can find out the equivalent stress. So you have the initial stress, you have the failure stress, and then also you have the equivalent stress. And also the maximum pass pressure, because you kind of like rebound on this point. So the change of the wall ratios and also the change of the stress. So we also work for both like a drain and undrain conditions. Then like through the mathematical equations, you can solve two equations. The change of the wall ratios based on the slope on the equivalence line, and also based on the slope, the slope of the overly consolidated line, which is the blue one, and also the slope of the green one, the virgin compression line, or the normally consolidated line, so they are the same thing. Then you can set up these two equations with respect to the change of the stress. So this is just a point slope form. So we also talk about this. So I guess everyone feel comfortable on the normal scales. So when you have a normal scales, the slope is equals to how you call it? The y's over what? The y's over the 1, right? Am I correct? So the y's over the 1, which is the delta y divided by delta x, which is the slope. But realize this, all the trick is just because you are on a semi-log scale. So you will do this a lot for homework 5, and I expect that you feel very comfortable on this, such that you can handle exam number 2, the midterm exams. You are on a semi-log scale. So the delta x now in log scale, so become log x, log x2 minus log x1. So and when you have a log scale, subtracting each other, it become a ratio. So at the end of the day, you get the equation is like here. It's just like a geometry in a semi-log scale, and the delta y is the change of the wall ratios, and the delta x is the change of the stress. And the change of the stress, you have within this equivalent stress concept, you can have initial stress, final stress, and also maximum pass pressure. And come along with it is the equivalent stress. So any questions on this point? Okay, so let's continue. So the whole thing here, again, this Dewey graph. So we have been keep working on this graph for how long? For 2 weeks already, I guess, even more than that maybe. So this two graph, and also you need to realize that you need to have a good observations that this Dewey graph actually links with each other. So here I do my best. It's really hard to draw for curve. Whoops. I'll try my best. Okay, so the green line is the normally consolidated line. And then the red line is the critical state line. So when you do it, your homework in Excel, then you know, the line and the curve, everything hopefully will make sense to you. And when you have a semi-log scale, then you get a straight line. When you unlock it, then you become a curve. So you get something like that. So you will get all this line over here. So everything kind of like both sides go to the critical state line. So from here, you will go to here, and from the normally consolidated line will go to the endpoint. So this is the equivalent stress, and the other one is the critical stress, and also the initial stress. And again, these three graphs, they can talk to each other, they can link the information to each other. So this is your initial stress. And this is your final stress. And this is your equivalent stress. So this is your failure stress, your final stress. This is your initial stress. And this is your equivalent stress at this point. So the delta E pi is the equivalent stress. And we do have a critical state line. And this is the failure point. So this is where we start, right? This is where we start, and this is an overly consolidated soil. And in undrained conditions, remember, like we talk about this, in undrained conditions, we will get a curve like this. What's a stress path? So we spent a fair amount of time on talking about this, like Tuesday and also like last week. So how the stress path look like on this case? Starting with the initial stress, we go that way. So because like this graph and this graph, well, same as this three graph, they can connect to each other. So we're talking about like from this point to this point, right? But this is the E log P space, but this is the shear stress and the vertical stress space. So realize the equivalent stress concept. Tell us there will be the mirror image go from the equivalent stress to the failure points, to the end points. So if we start here, there will be another equivalent stress state to go there too. So one is being at a overly consolidated state. The other is a normally consolidated state. They both go to the endpoint. So that is the stress path. And this is the undrained shear strength of the soil. So which means at the equivalent stress, the undrained shear strength for normally consolidated soils will be equals to the the shear strength of overly consolidated soil. And the equivalent stress can be found out with these equations. So it kind of like becomes a mathematical model that you can find out the equivalent stress based on the initial stress, the stress history, and also the soil properties of the C sub C and C sub R. Any questions on this? Okay, so moving on. So the critical state soil mechanics, in summary, the ratios of the undrained shear strength over the vertical effective stress is a constant for the normally consolidated soil. So this is true. This is also true for Chansap. So we have done homework number 4 on that, where I'm start about to grading it. So this is kind of like a true, also consistent with the Chansap concept, and on the virgin compression line. So we could find an equivalent stress that equals to the initial stress from the overly consolidated state. So if this is at the NC state and this at the OC state, such that like if we normalize, if we substitute this initial stress with the equivalent stress, we can find out a constant for both like an NC and OC soil. And for simple shear testing, so we keep talking about this is equal to constant. And for simple shear testing, this is the constants that we can find out. So it's powerful in a sense that if we can find out the friction angle, then very likely we can correlate that with the undrained shear strength. And one more time, it's like as we have proven that in the previous slide, the equivalent stress is equals to the vertical stress times OCR 1 minus the ratios of the recompression index and compression index. And for the so it has been proved by the from the direct simple shear testing. So this is from direct simple shear testing. We substitute like the ratios over there. SU over vertical stress will be equals to 1/2 of the sine 3 pi times OCR to a constant. And this constant is 1 minus C sub R over C sub C. So this works for simple shear test. So this works for simple shear test. And the next graph is the experimental data that we talk about. So they got a theory, and then like they have a experimental research program, and to prove that in fact, there's a linear relationship between the constant we talk about with the sine phi angle. And you also work for like all different kinds of soil. So this is different, like kind of like a clay around the world, and we prove the linear relationships. So which means in another way is the whole critical state soil mechanic works and the chance-out model works, and we prove that experimentally. And when we try to bring in like more data and combining more data and then play with like different friction angles, and we find like the friction angle from 20 degrees to 4 degrees, and like we also observe those like linear trend on that. So which means like that this critical state soil mechanics, it works for pretty much like every soils worldwide. So pretty much we talk database here is a lot from the United States, Asia. So Bangkok is Asia. So Boston Blue Clay is United States, and the Chongham soils the Drammen soil is from Norway. So pretty much like they work for everywhere. So last but not least, let's wrap this up with the next steps. So we have been talking about critical state soil mechanics, and pretty much it's just for soil modeling, for numerical modeling for ground behavior. The critical state soil mechanics is just a very simple first page of like maybe a thesis of research thesis. So this is just a starting point, and the next step to build up on this work of soil modeling is what you try to achieve here is through this model, try to predict or try to develop a yield surface for soil. So if you have been learning from material mechanics, steel, like for example, concrete or steel, I think steel is more common. You learn about how to model the yield surface of steel. For example, the von Mises model, if you still remember that, and the Moore Coulomb model, we keep talking about at the beginning, both for physics and also for this class. That is also like a model trying to capture the yield surface of material. Actually, like soil mechanics, we borrow like the Moore Coulomb model from the metal mechanics. So now soil is much complicated than like a homogeneous like material like steel or even concrete, because this is highly nonlinear and plastic material. So which means like it's really hard. It's really hard to capture, to model it, and the critical state soil mechanics help. So the yield surface, the way that we connect with critical state soil mechanics is, for example, when we have multiple soils testing. So one more times. So we do this the one last time. So we have the normally consolidated line. I promise you this is the one last time we do this together. And now we have the critical state line, and we have the rebound curve. Right there. And then if we have like multiple, let me put this a bit longer. You have multiple like soil samples. If we have like this 3 tests, both from the start from the overly consolidated line. So when you fail, we know that you know where it starts, we know where it ends. You always want to go to the critical state line. So when you are like left to the critical state line, you go to right, and you're right to the critical state line, you go to the left. for undrained loading. So you go this way, you go this way, and this one you go this way. And for normal scales, so now become a curve. And again, the whole three graph, they can talk to each other. So we have this point to go to here. And we have this point to go to there. And we have this point. Whoops, I messed up. I didn't draw it well. Let's say you go here. Just make the change. Yeah, how should I do this? Maybe let me erase my blue line here. See, we bound like this. No, it's not helping. Let's do something like this. So when you rebound at the other side, oops. Go from here, oops. To there. Oof, I think this is the most difficult part that I need to draw. So we go this way, and this part will go this way for the stress path. And then like you can link with the critical state line. And all the stress, they are kind of connected. So this is where we start, stress path number one. This is where we start, and this is where we end. And it is at the overly consolidated side, and then like I pretty much like I generate like a positive excess pore pressure. So you will go this way. So very similar for the second test. This is where we start, and this is where we end. So we go this way. And then for third test, you know, you have a contractive behavior instead of dilative behavior. This is where it start. This is where it end. So you're not generating excess pore pressure. So this is kind of the extreme case, even for overly consolidated soil. Yeah, the stress level that you start with is so high that you're not generating like you're not having like a dilative behavior, but you have a contractive behavior, because the critical state soil mechanics, the whole thing tells us this depends on both density and also stress. So this is rare, but you can also happen. So you have the stress path look like this. So we are talking about the yield surface. So the yield surface will be the one that like to capture all the stress path, such that like a 3 dimensions, you can predict, like you can define the failure surface at more dimensions, capturing all the like other state of the soils, like the density and also the confining stresses. And this will be the yield surface that I talk about. Oops. So this critical state soil mechanics kind of like lay down the framework, allow us to develop the yield surface for different type of soil. So soil type number 1, we have yield surface that are very different than like the yield surface that is second type. And it allows you to have a 3-dimensional dependency on that, both the void ratios, the stress, and also the shear stress. And you can allows you to able to model complicated like a behavior, not even just not like a elastic, not just plastic. So simple elastic, simple plastic, or perfectly elastic, perfectly plastic material is easy to model. So you remember what is like a simple elastic, right? Just like a line back and forth, like a constant slope is simple elastic. Simple elastic, perfectly plastic. So simple elastic, and then perfect plastic will be a material like this. So this is simple elastic and perfect plastic material. When we talk about like a stress and strain relationship. So this is back to your mechanical material class, at undergrad level, you should have learned about all this. And the simple elastic is just this, right? Just back and forth straight line. So this is simple elastic, but soil is very complicated. You get a curve, so you get like a highly nonlinear stress strain curve. So that's why it's very hard to model. Because if you want to capture like like the behavior like this, you just need like a 1 parameters, right? So this is the elastic model, perfectly simple elastic model. And when you get to the simple elastic and perfect mass plastic model, is got a little more complicated. You need to know the strain level, the yield strength, and you need to know the slope of this part, and also like the yield stress. So this is kind of like the yielding surface that we talk about, just a linear, just a plane, a line in 2D, but a plane in 3 dimensions, like modeling role. So pretty much you need like 3 parameters, and then like a simple elastic, you just need 1 parameters. But for the case of soils, you need many parameters to be able to do it. So that's why you need some solid like a framework or platform. Think if you're a computer guys, like think computer engineers, think about it as kind of like the OS system, kind of like a platform to get started. And the critical state soil mechanic is the platform, because you cannot have infinite parameters to work on it. Well, like some famous model like MIT S1 models and other models, they have 50 parameters. Try to model this type of behavior for soil. But like critical state solid mechanics to give you a platform, a framework to start like getting away from like too many parameters, but a framework from where you start, where you end, to give you like some like guidelines or some like directions to model this yield surface. At the end of the day, that's what we try to work on. So any questions on this? If you find this interesting, always find this interesting. If you find this interesting, I highly recommend you go to grad school, get a PhD. And then if you do spend enough time, then like, you'll be able to build a new model based on the critical state framework. Questions? I got questions.
Dr. Kwan?
Yeah, go ahead, David.
Hey, so I have two questions. The first one
Sure.
is, how is this related to pre-consolidation? It says yield surface represents 3D pre-consolidation. What does that mean?
Yeah, I think I forget where the frankly I forget where the presentations pre-consolidation come from. Yeah, I maybe it shouldn't be there.
Okay.
Yeah, good catch.
No worries.
So 3D space is what it means.
Okay. Yeah.
Yep. Second questions?
My second question is, so like what's the significance of the equivalent stress concept?
Very good, very good, very good. Well, this is very likely for modeling work.
Okay.
In modern work, you need a bridge or you need like another stress state to mirror what you work. And actually, the need of the equivalent stress is given examples on the next slide when we talk about the DSS. So the equivalent stress allow us to bridge the like overly consolidated side, side, and also normally consolidated side, such that like we can substitute the vertical stress with this equivalent stress right there, and then with this substituting this equivalent stress, we can plug in the formula we got right there, and then end up we can like solve for these equations. So that's one of the use of this equivalent stress. And the way I look at it is more like a mathematical mean for us to eventually solve for the problems that we want to find undrained shear strength. So you see throughout this like kind of like this like a procedure, it helps you to bridge to find the undrained shear strength with the solved parameters right there. So that's the good use of equivalent stress.
Okay.
In practice, like you don't use this as much, rarely. But if you work on a high profile project, you need to think outside the box. That's maybe the time that you will need equivalent stress. Day-to-day job, you won't see it. But if you have truly a modeling guy or solid mechanic like an expert, then you may at some projects it may become useful.
Okay, thank you.
Sure. Any more questions? If not, then like I think are we done on this? Well, the end of it is just kind of like a recap, and also like I think at on Chance App we talk about this project at like a port of Anchorage, Alaska. What happened? So pretty much like this another like a real life, put it there just because another real life project that we do use critical state solid mechanics. I think like as some high profile project, I don't think you will use that a lot from a day-to-day project, like a mid-size project. You don't even like don't want to go that wild because a conventional geotechnical like approach can solve your problem already. So you don't bother to bring in a solid mechanic expert to do stuff like this. But getting to some project like mining, I know mining people, they use a lot of critical state framework to solve for the engine design, because pretty much like critical state solid mechanics means you need to define the three lines right there, the green, red, and blue. The normally consolidated line, critical state, and also the overly consolidated line, and which means expensive laboratory testing. And expensive laboratory testing means the expense in retreating undisturbed soil, which is not cheap. So if you have a high profile project, very likely from the consulting side, then that's the way to go. And a project like this, like an offshore, like a oil platform, they do a lot of, they do have a lot of black money that comes in. So it makes sense. They would spend the effort to develop all this critical state framework right there. So this you get critical state line on the left right there. So you get the PQ, pretty much the orange line is the critical state line. So to wrap this up, well, I don't think I need to repeat it. So this is pretty much we have been talking about it. The initial state. So this is kind of repeating some of the previous slides. So I don't want to spend the time to repeat this. But if you go back to the previous slides, you will find the same informations. So the initial state. So again, it's about the simple. Well, mathematical wise, it's just at this point, you just the jump. What's the term? Simple algebra. A point, a slope, then you can set up the three lines. The point will be the initial state, void ratios, and also the void ratios, and also the stress state give you 1 point. And the slopes are the soil parameters. So just like we learned in 366 geotechnical engineering course undergrad level, we talk about the compression index, we talk about the recompression index, we talk about the tangent phi, which is the tangent of the friction angle, give you the failure envelopes. Those are the slope that you need. A point, a slope, then you can form the lines. And then the next thing will be you need to understand the stress path, how to get from a starting point to the end point. Are you expecting a horizontal line because this is undrained conditions, or are you expecting a vertical line because now there's no generations or excess pore pressure, being a change of volume, so change of void ratios. So the end point and start point. and also on the shear stress versus vertical stress space, what kind of curve or line is expecting that require understanding on the pore pressure development. So just like what we have talked about on Tuesday. So when you have start point, end point, how this curve get to it from the start to the end is also require understanding on how the pore pressure generated based on the stress state. Are you expecting dilative behavior or compressive behavior? Are you expecting generation of excess pore pressure, positive or negative? So putting all this together, that's the critical state framework. And we work through our simple examples, also use the Griffin stress concept, how to set up a simple mathematical model to predict the soil strength. So that's a good use of critical soil mechanics examples too. So this is one of the examples that we cover in this slides. So we talk about how to apply critical state soil mechanics to kind of a real engineering problems. You have a framework, make use of the what I have done. Based on the critical state framework, and then the Griffin stress concept will give you a undrained shear strength predictions right there. So that's one very simple use of the framework. But the next step, moving on, if you get the research site, or you get in the very high profile projects, you are the numerical expert, numerical modeling expert, numerical modeler, or the soil mechanic expert of your office. Then you will talk about how to develop the yield surface for the particular soil we work on your work sites. All right, any questions? If not, then we shall move on to work on examples problem together. Okay, so I have kind of like a sample problems on putting on Canvas, and along with it, I also upload the solutions. Oops, for the spare sheet. So I think it's this one. So this is my solutions to the problems that you're seeing. So let's see if I can do this. Let me try to zoom out a little bit. Would that be too small? Can you guys see? Able to handle this? Take away this part. Hopefully not too bad. Is the font size too small? Can you guys still able to see on screen? Okay, I assume you guys can see it. Okay, I got a thumbs up from Tommy, which is good. Oh yeah, you guys are chatting. Okay, very good. Oh, someone is getting hungry. Okay, so like 25 more minutes, hang on there. Oh, so that's questions. Go back to slide 15. Oh, Amber, do you still want to go back to slide 15? Sorry, I missed your questions on the text box. Okay, all right. Then let's look at these examples together. So first, we talk about like there's a sample. So examples we call SCO1 is taken from a depth of 10 meters below the mud line, and upon consolidations to restore the stress ratios to in situ values, the specimen is normally consolidated with an initial void ratios of 1.10. So again, like we talk about the stress state, the 1 point. So this is one part of the points, the y-axis, right? We talk about, because critical state solid mechanics at the end of the day is based on the informations we have. So when I say information I have, that means the laboratory test results we obtained from the field and then to the lab. After we have the lab results, then we should able to construct all these three lines. That's our goal. So first of all, we know like the initial void ratio is 1.1 respective to effective vertical stress of 80 kilopascal. 80 kilopascal. So that's what we try to work on, right? So that's our first point. So we know that the E naught. Let me see how to do this. Let me do it here. Well, do it here. So the E naught is 1.1, and the vertical stress that come with it is 80 kilopascal. So this is our initial stress state. And then like you also tell us the virgin compression index, which is the compaction index, is 0.5. So this slope. Now we have a pond and we have a slope. Then we should able to construct which line. So which is this information is representing? I want you to think about it. Anyone? You can either like speak out or like type your answer in the text box. Yeah, NCR, very good. This is the normally consolidated line. So with a point with a slope, we can construct a green line. So I use green, like, doesn't mean like the rest of the world, everybody use green, but I just try to be consistent through this lecture. So which is the normally consolidated line. So we have that. So the first question is draw the initial stress state points and then draw the virgin compression line, which is the NCL, throughout the E-log space. So now is the the matter of constructing this like a green line. So this is the Excel spreadsheet should be available online. So I expect you know how to do this for these examples and also do it for your homework. And again, we take advantage of the equations, right? If you go back to your 366, your soil mechanics class, we learn how to calculate the conversion index, C sub C, which is the delta Y, the change of the Y ratios over the change of the X, the delta X. And this is a sloping down, it's a negative slope line. So that's why it's a negative right there, negative one right there. So this is the E naught and also the conversion index. So this is the stress point that I talk about right here. This is the stress point that I talk about here. So E naught is 1.1, and then like this is also the initial stress. So now the matter is how to construct this green line right there. Is you know one point, and also you know the slope, then we should able to calculate the rest of it. So now it just become mathematical problems, how to create the straight line, right? So what I would do is like this is 1.1, and I make a discrete like a different points, like smaller and greater than that. So I make up those points, 0.5, 0.6, 0.7, 0.8. You know, you can say 0.4, 0.5, 0.6. You know, up to you. Or you can say 0.5 and then 0.55 and then 0.6 and 0.65 and then so forth and so on. So you make the spacings that you want to represent to capture the green line right here. And that now it's just pretty much just solving the equations, how to get so this is X coordinate, and now this is how to solve for the Y coordinates. So if I do it here quickly, I know some of you know how to do it, but like I don't want to lose anyone. So let me try to do this with you really quick. So we know this equations. So if you have any questions, try to stop me. So this is the equations, right? And if we try to plug in the, handle the negative values, this is what we got. And then we organize the equations. And then we further we organize the equations right there. This is what we have. And the whole idea is we want to solve for sigma 1. We want to solve for sigma 1 because we know that we can assign sigma 2 to be 80 kilopascal. We know the point, and the corresponding E2 is 1.1. We know C sub C is 0.5. So if we look at these equations again, we know we try to solve for sigma 1. We know sigma 2 is 80. We know like a E2 is 1.1. And we know E1. E1 is all the values that we just assigned. So E1 will be equals to so the values right here, 0.5 to 1, and 1 to 1, 1.2 to 1.5. So what we are trying to do here is try to solve for the sigma 1 corresponding to those E1s, could be 0.5, 0.6, 0.7, 0.8. 1.5. So if we further work on these equations, so this is what we know, and then we solve for sigma 1. So sigma 1 over sigma 2 Then we need to unlock it. So you do the 10 power for each side. So sigma 1 will be just equals to this number here times sigma 2. So whatever I do here on this calculations, so this calculations right here will be same as this formula here. I hope it's clear. So any questions? So you try to work it out, go ahead, try to work it out. I'll practice it like without looking at my spare sheet and see whether you can do it yourself. You need to do it here, and also you need to do your homework, and I guarantee you need to do it for exams here. But the basic concept, this is just like a simple math. If you need time to refresh your algebra skills, that's what I recommend you just crack your algebra textbook. But like the concept here, the geotechnical concept that we're trying to learn here is, a pond, the pond which is the stress state, and where's the pond come from? Is from lab testing. Is representing the initial state of your site. If you're think about your house right now, right, sitting on a soil profile. If the soils of the foundations of your house is, you have a density, which means wall ratios of 1/1.1, then this 1.1. If the stress state adding on that is 80 kilopascal, you represent the initial stress state of the site is 1 pond, and then you also want to know the slope. So the slope will be the compression index. So the geotech concept here is like a pond, yes, initial pond, initial stress state, and the soil properties, which is the compression index of of the soil you're working on. A pond, a slope, then you can form the normally consolidated line. And under the critical state framework is the starting point, is where you start. Okay, any questions here? So I don't want to lose anyone. If you get lost at this point, pretty much you will have a hard time throughout the whole problems. Easy? Geotech is easy, right? Okay, so that is question 1. So
yeah. So I had a problem here with my internet, so I couldn't hear you well. Could you go very briefly on the exercise again?
So you mean how to get the green line, right? So what we try to do here is we know a pond. So this is the pond. Y ratio is equal to 1.1, and the vertical stress is 80. We know a pond, and we know a slope. And then we try to solve for the rest of it, because what we try to achieve here is try to draw this green line. To draw this green line, we know our pond, and we know the slope, and the math equations here is try to devise how to solve for the green line. So if you want to catch up, you can go back to the lecture, or try to read through this math right here. So nothing too hard. It's pretty much just try to prove to you how to do these calculations right here, based on the concept of pond slope from semi-log scale.
Okay, thank you.
Okay, sure, no problem. And again, I hope this time we can successfully record the lecture so everyone can go back. And the bottom line, I will upload my lecture slide so you guys can go back and look at it too. So that pretty much is question 1.1, and questions 1.2 is I say pick several points on the virgin compression line and scale this over to draw the one that without the log. So this is what exactly I do. It's the same plot. So this two is identical, except the x-axis is not in log scale. So if I unlock this x-axis, we should get back the same curve. So this is how it looks like when I unlock it. So here's a curve. But if you like do a semi-log scale, then you will become a line, a linear line. So that's why you can take advantage of the slope, C sub C and C sub L, C sub C and C sub R. So that's 1.2. 1.3 is asked you to estimate the critical state line with the same slope, because you know the critical state line is parallel with the normally consolidated line. And like this gives you some help here, you know, in the real world is, you know, you need to do it like for a couple tests to find out like the failure points. But here, just try to help you, tells you the stress is half of the virgin compression line. So, well, this is just because this is the very first example problem. So try to make your life easy. You know, I take a half. In the real world, like, you know, it's not necessarily half. It could be like, depends on soil type. It could be like a 0.4, it could be 0.6, it could be 0.55, depends on the soil type. So, but like to find this out, like in practice, you need to do a couple like advanced laboratory testing to find out the ratio, because you know, like the two lines is parallel. So the difference between the two is always a ratio, but how much you need to like spend the money. When you become the engineer, you need to convince the client, pay for it, so you can find out the ratio. So the ratios right there. So this is pretty much is SU over the related to SU over the vertical stress ratio. So here is Terry is just half. So this is my normally consolidated. When I construct this is my normally consolidated line, and this will be my critical state line, and you will be just half of the normally consolidated line. So I divide the whole thing by half, then I will get my critical state line. So the same graph, if I if I unlock it, then I will get a curve right here. So pretty much that's 1.3 and 1.4. So 1.5 here is ask you, you have a specimens. So this is a second specimens. Is also as you know, normally consolidated state, and then like you said, like you consolidated to your void ratios of 0.7, and then ask you to draw this initial state, initial stress state on all three space, and what is the corresponding like initial stress. So we know a void ratios of 0.7. The void ratios of 0.7 over here, right? Can I draw on this? I think I can draw on this, right? Excel. Or I can animate here. Right, yeah, very good. So this is 0.7, right? It's right here. Can I use other color? So sorry guys, this is my first time using this tool. Let me try to use other color. I use orange right here. So we are saying 0.7 here. And the corresponding vertical stress will be this point, right? And we are at the normally consolidated line. So the corresponding stress of that is 200, 300, 400, 500 is 500. So that the corresponding initial stress here is 500. Kilopascal. So now it's a specimen is then you share like to drain conditions with a measured vertical stress at failure, and then ask that to plot this stress path in the shear stress space, and pretty much now tells you the specimen fell at like a stress of 282 and friction angles of 29, and the cohesions is 0. So this bring it up to doing the oh, sorry, I think before I move on, I better erase what I've drawn. Oops. Okay, so pretty much this is the critical state line. So it tells you it has friction angles of like a 29.5 and the cohesions of 0. So pretty much this is the critical state line. And when I construct this critical state line, all I need is the slope. So I discrete like the vertical stress space. So this is like kind of like x-axis. I space around 100. It's up to you if you want to say 50, 100, 150. If you want to say like 200, 400, 600, it's up to you. But this is my x and this is my y. So again, it's just like algebra problems. And now even at a normal scale, not like semi-log scale. So you know like a pond, so those are ponds. And if you know the slope, and the slope is related to the friction angles, and you can count the friction angles is given there. So for the given like stress, you know the pond and you know the friction angles, then you can find out the corresponding shear stress. So that's what we have been doing right there. Well, I only have a couple of minutes. I don't want to go through the whole thing because I do want to finish this today. But what I want to mention is like to have you. Oops, no, not this one. To have you try the homework problems. Example problems is home, and like pretty much like the rest of it is just asking you predicting the stress state. Like this now you have a new task. You are doing drain loading and you're doing undrain loading. What is where to start and what is the end point, and at failure what are the stress state. So I do want you to try that. But before we go to conclude this, I want you to and also at some point of the problems also talk about the overly consolidated line. I want you to try that too by yourself too, because again, like one pond, so the pond is likely where you do the rebound, which is this pond, and the problems, the question problem giving you the slope, which is the C sub R, which is also like called C sub S. So C sub R is equal to C sub S. They are the same thing, because the convection index is the same as the swirling index. So the slope, which is 0.1, and a pond, then you should able to construct this overly consolidated line right here. So the stress and the Y ratios, and then you can find out this line. So pretty much the rest of the problem will be just ask you after constructing all this line, we'll ask you like at different stress state, where you start, and then predict what is the final stress.